We are starting week number 3 from this lecture. In this week, the first lecture is about chapter number 3, which is more specifically, we are studying section number 3.1. In this section, we will discuss what exactly is an optical fiber, how it is made. We will discuss some critical angles. We have already discussed the critical incident angle in the previous lecture, and we will define a term that is called numerical aperture, and we will also discuss few examples to support our discussion. So first, let's see what an optical fiber is made of. So maybe with discussion casually among your friends, or looking at Wikipedia, or surfing internet, or maybe having this general knowledge, you might know that an optical fiber is actually a cable, or as it's called, an optical fiber cable. But this cable is not particularly same as a typical cable for carrying current, because there is no conductor inside this cable that can conduct electricity. In fact, the carrier of the wave in this case is actually this medium, which is made out of glass. So this innermost medium of the cable, that is actually called the fiber core, which carries the light or carries the electromagnetic wave in this cable, is made out of glass, and more specifically it is called silica. Okay, so as we discussed in the previous lecture, that this silica has some high refractive index. So whatever the refractive index is, which we usually refer to as the number n, we give it a variable n. So the refractive index of this core is higher as compared to its surroundings. So now you might notice that this optical fiber, which has its core made out of silica with refractive index of say n1, okay, so I'll write n1 over here, it is not surrounded by air. Okay, in fact it is surrounded by another medium which is called cladding, and this cladding has a refractive index of n2. Interestingly, this cladding is also made up of silica, but the difference is that it has higher refractive index. Sorry, it has lower refractive index. Okay, so n2 has lower refractive index, so n1 is actually greater than n2. Okay, so the core has higher refractive index as compared to the cladding surrounding it, and you might notice from these numbers that the diameters of these cables, which is the core and the cladding, and in fact the coding and other layers, is very small, some micrometers. So each fiber optic cable is actually a very small cable as compared to a typical electrical cable that is usually made out of copper, or even if it's some other material, it's usually much thicker than this. So this fiber optic cable has these two very important mediums, its core and its cladding, with the core having more refractive index than the cladding. And then we have some coating on top of it, and we have some buffer space, which is another material, and we have some strength materials such as Kevlar or other materials that actually support this structure inside it and does not allow it to bend too much. And at the outermost side we have a jacket, which is usually kind of a rubber, or you can say a polyurethane material. So this is the construction of this optical fiber. Okay, this core, as if you notice again, for example, the popular diameters that this core might have, depending upon different wavelengths or different purposes, the core could be of 9 micrometer, 50 micrometer, 62.5 micrometer, and the cladding may be of 125 micrometer, and so on. And these fiber optic cables can also be made out of plastics. So in a typical application of short purpose communication, short distance communication, the cable might be made of plastic and not silica. So that is also possible, and this core might be made of plastic. Okay, of course the core and the cladding both would be made out of plastic, but again the refractive index of core would be greater than the refractive index of the cladding. So in the previous lecture we discussed that it is important for the light to remain inside the cable. So for this light to remain inside the cable, we discussed that we want to adopt this phenomena inside the cable that is called total internal reflection, which is that when light falls on this surface means this is the core with the refractive index of n1 as mentioned over here. So the core has high refractive index n1, and the outside cladding has a lower refractive index of N2. Okay, so this is a denser medium and this is a lighter medium. So when light travels from a denser medium to a lighter medium, it can reflect out of this medium into N2, and it might also reflect back into this medium. Sorry, it can refract into the next medium, and it can reflect back into this medium again in N1 if it is observing total internal reflections. And we discussed that uh, if this angle which is known as the incident angle is greater than the critical angle, then we will not experience any refraction in the next medium. In fact, we will experience total internal reflection in the same medium back. Okay, so if this angle of incidence, so I've drawn these three angles of these three different waves. So if these angles are greater than the critical incident angle, then light will be trapped inside this medium. So for this example, we have N1 equal to 1.48 and N2 equal to 1.46. So how can light be trapped inside this fiber optic? Again, if this angle is this angle is more than the critical angle. I hope I have not made a mistake in the previous comment. If this angle is more than the critical angle, then the light will experience total internal reflection and it will be trapped inside the fiber optic. So in the previous lecture, we found out this formula for using Snell's law for critical angle. So we are using the same formula. So as per the book, we are using this notation to describe the incident critical angle. Okay, so this is the critical incident angle. Okay, so this is how we write it with the theta. So this is equal to sine inverse N2 over N1, where N2 is the refractive index of the second medium and N1 is the refractive index of the first medium. So we already know these values. We just plug them inside this function, and the angle that comes out is 80.57 degrees. So which means that this is the normal, and if this angle is more than 80.57 degrees, then we will experience total internal reflection inside the fiber optic. Okay, so we need angle more than this critical angle, which means that if the angle is something like this in this direction, and for example if this is the ray that will be reflected or may be refracted, then this ray needs to be more flatter, which means it should be traveling in more among these angles as compared to these angles, because if it travels in this angle, then this angle is very small compared to the normal. So this is not greater than 80, this is very small angle, maybe 20 or 30 degrees. So it is not greater than the critical angle. We will not experience total internal reflection. So the lights need to travel more in a flatter way, so that we can have this big angle more than 80.57 degrees to make sure that it experiences total internal reflection. Okay, so this is an easy way to understand this critical angle, that light needs to travel more in a more flat manner as compared to in this more sharp manner like this. Okay, so these kind of rays of lights might not experience total internal reflections, and they will be uh, refracted outside this medium. Okay, so this is how we trap the light inside the fiber optic. So we have discussed this critical incident angle. Okay, so we called this angle critical incident angle because this was the angle that the ray of light made with the normal across this boundary. Okay, so there's another critical angle which is called critical propagation angle. So this angle, and we refer to it as alpha c. As per our book, you can give it any name, but as per our book, we are following the text and it tells us to use this variable. So we call this critical propagation angle, and this is the angle which the ray of light will make with a center line in the optical fiber. So this is the center line in the optical fiber. This is not some practical line or physical line drawn on the cable. This is just an imaginary line, so it is drawn in this dotted way. So this is an imaginary line, and when we were talking about the critical incident angle, we were talking about the ray of light making an angle with this normal. Okay, so that was the critical incident angle. The critical propagation angle is the angle that the same ray of light makes with this imaginary line in the center of the cable. This is the critical propagation angle. So as you can see probably very clearly that since this is the direction of propagation, so this direction of propagation is being compared with this imaginary line. So that is why we called it propagation angle. And since this line is actually incident on the other medium or the boundary of the two mediums, we call this angle as the critical incident angle. So we have critical incident angle over here and critical propagation angle over here. So I hope you can differentiate between these two angles. Okay. So if you notice from this figure that we are interested to find out alpha c, because we have already found out using Snell's law this critical incident angle. Now we would want to find out this critical propagation angle. So you might notice that this is actually a right angle over here. Okay, I'll draw it again over here. So this is actually a right angle. Okay, so I've drawn a neat right angle over here. From the properties of triangles, from the geometry of triangles, if you remember from your geometry classes in mathematics, you might remember that this a triangle actually has total angles of 180 degrees. So for a right angle triangle, this angle is obviously always 90 degrees. So we know that this angle is 90 degree, and the remaining two angles can be found out by using their differences. So if this is 45 degrees, then obviously this is also 45 degrees. If this is 80 degree, if this is 80 degrees, then this much must be 10 degrees, and so on. Okay, so these two angles can be found out with their differences. So if this is A, this must be 90 minus A. Okay, or if this is A, this must be 90 minus A, because the total angles are equal to 180 degrees. So we already know this angle because we are calling this angle as critical incident angle. So if you want to find out this angle, which is the critical propagation angle alpha c, so it can be found out by 90 minus this value, the critical incident angle. Okay, so this is a very easy to understand formula for finding out the critical propagation angle. So if we have already found out the critical incident angle, the critical propagation angle is very easy to find. It is just 90 minus critical incident angle. Okay, so now that we have mentioned two critical angles, we cannot say critical angle only, because it might confuse us if we are talking about this incident angle or this propagation angle. So we have to mention if we are talking about the critical incident or the propagation angle. So this is the angle, okay, the propagation angle. So as we discussed in the previous lecture, that to maintain total internal reflections, this angle has to be greater than the critical incident angle. And in this first slide over here, first example over here, we found out that the critical incident angle was 80.57 degrees. So we say that for this example, this angle, this critical angle is 80.57 degrees. Okay, so the angle of the light needs to be more than this value to maintain total internal reflections. So when this angle is actually more than 80.57, what do you think will be the angle of alpha c? So we already know that we take the difference of 90 minus the critical incident angle, which is 80 minus 0.57 degrees. So when the light makes an angle of more than this value, then this value will actually become smaller and smaller. So as the light falls on this surface more flatter, this angle will actually become smaller and smaller, and this angle will actually become greater and greater as almost approaching 90 degrees. So this is almost approaching 90 degrees, and this is almost approaching 0 degrees if the light is becoming very flat. Okay, so anyways, we have to make sure that this angle is this critical incident angle is not less than 80.57 degrees. So it should always be more than 80.57 degrees for this example, and that means this angle would always be less than this value. Okay, so the thing that you need to remember is that the critical incident angle should be higher than a certain amount, and the critical propagation angle should be smaller than a particular amount. Okay, so we know how to find out this critical propagation angle. We just discussed it. Now to express it in in terms of cosines, we just take a cosine at both sides of this equation. So cosine alpha c is equal to cosine of 90 minus this critical incident angle. Okay, so on the right hand side I can use this trigonometric identity. It's a very basic identity, I'm sure you all remember it. So using this identity I can simplify this right hand side, and now on the right hand side I have cos 90 which is equal to 0, and I also have sin 90 which is equal to 1. So on the right hand side I'm only left with sin theta. Okay, so we have already find out this value using Snell's law for critical incident angle, and that value was equal to n2 over n1. Okay, so this means cos alpha c is equal to n2 over n1, or critical angle, the critical propagation angle, is equal to cos inverse n2 over n1. So this is the formula that you can use to directly find out the critical propagation angle using the values of second refractive index and the first refractive index. And to even have a better representation, we usually, since in the first formula of this critical incident angle we have used sine, not cosine, so we would try to express this function as sine instead of cosine, and that is very easy to do because we have another identity which I'm sure you remember also, is that we can also express sine with a cosine or cosine with a sine if we take one variable at the other side of the equation. So since the angle is called alpha c for us, so we are not using the term theta, in fact we are using alpha c. So sin alpha c is equal to square root of 1 minus cosine square alpha c. So we took cosine to the right hand side of this equation. Okay, and from the previous page over here, remember that cosine alpha c is equal to n2 over n1. So this cosine is equal to n2 over n1. So we just plug in this value, and this is the result that we get. So to find out the angle exactly, we just move sine over here. So to find out the critical propagation angle, this is the term or the formula that you will use to find out this critical propagation angle. So this is the formula for critical incident angle, and this is the formula for critical propagation angle. Okay, again both of these formulas are using only two variables, that is n2 and n1. That's it. So now that we know the both formulas and we have the understanding of both these values, the critical incident angle and the critical propagation angle, we want to point out the significance of these values. So in the previous lecture we discussed that this critical incident angle, okay, so if this was the angle, suppose if this is the critical incident angle, in the previous lecture we discussed that this criticality must be maintained, which means that your angle should always be, the angle of your light should always be greater than this angle. So it should be greater than this angle, okay, the critical angle. So in the previous lecture we discussed that this criticality, this critical incident angle must be greater than this critical incident angle. Okay, so the what I mean to say is that my incident angle should always be greater than the critical incident angle to maintain total internal reflections. Okay, now that we have already also discussed the propagation angle or the critical propagation angle, I can extend this definition and I can say that if this ray of light makes an angle with this imaginary line in the center of this cable, and I call this angle as propagation angle or critical propagation angle, then I need to make sure that the angle that my light or my ray of light makes with this center line, it should always be less than the critical propagation angle. Okay, so if I ensure that this angle is less than the propagation angle that my ray of light makes with the center line is less than the critical propagation angle, then it automatically means that it will have this incident angle greater than the critical incident angle. So the criticality will be maintained if I just make sure that this angle is not violated. Okay, then I will have total internal reflections. So this is how I can ensure just by looking at my propagation angle. Okay, so to discuss this example, just if we need to find out the critical propagation angle. So we use the formula that we just derived, plug in the values of n2 and n1, and we find out that the critical propagation angle is 9.43 degrees. So it is from the same example that we discussed previously. We have the same refractive indices. So last time, in the previous example, the critical incident angle was 80.57 degrees, and now if you just notice, the critical propagation angle is 9.43 degrees. So 9.43 plus 80.57 is equal to 90 degrees, which is of course is true, because in a right angle triangle, the sum of all these angles should be equal to 180 degrees. So the third angle, which is missing right now, is in a right angle triangle, is obviously 90 degrees. So we have 180 degrees. So we can just verify that we have not made any mistake. Okay. So now that we have discussed this critical incident angle, and we have discussed this critical propagation angle, there's a third important critical angle that is called the acceptance angle. Okay, so we started from this point, then we went to this point. Now we are trying to get to the beginning, where the light is actually entering the fiber optic cable. So the previous exercise that we were discussing, we were trying to trap the light inside this cable, but now we are actually trying to enter the light inside the medium. So if you remember that this is light and we call this N3 because we have already called this N1 and we have called the cladding N2, so let's just say this is N3. So the N3 is typically air, because the light enters from outside the cable, and outside the cable there is gap between the source of the light and the cable. So that gap is actually air. So air is a very light medium and the core is actually a denser medium, so N1 is higher than N3. Okay, and if you remember from the previous lectures, which you should, that from when a lighter medium, so this is a light medium, when from a lighter medium light enters from a lighter medium to a denser medium, it refracts towards the normal. Okay, so if you notice, it is not moving away from the normal. Okay, this is the normal, draw in dotted line over here, because this is this is first medium and this is the second medium in which the light is entering. So this is the normal from the surface. So the light is not refracting. This is how the light was coming in. So it is not refracting away from the medium. In fact, it is refracting towards the medium. Okay, sorry, towards the normal, not medium, towards the normal. So this is what we discussed from the previous discussion. So we know that this will happen when the light enters from air in this core. It will bend towards this normal, but when it bends towards the normal, obviously it will make an angle with this axis, which as you know right now, it is called the propagation angle, and this propagation angle should always be smaller than the critical propagation angle to make sure that this critical incident angle is also achieved. So do all the ray of lights actually achieve this requirement or not? So we can actually go backwards from incident angle to propagation angle to this acceptance angle to learn if all the light will actually experience total internal reflections once it enters the medium or not. Okay, so let's just discuss the importance of this alpha, which is acceptance angle. So I've taken this picture from somewhere else on the internet. So in our book, alpha is known as the propagation angle. So we call this angle from our book as theta A. Okay, so this is the acceptance angle, theta A. Okay, so as per our book, the acceptance angle is the angle which the incident ray makes with the center line. Okay, so this is the center line, again the imaginary line. This is the light source, and this is the angle that the ray of light is making with this normal. Okay, so when the light enters the second medium, it will refract towards this imaginary axis or towards the normal. Okay, and again using Snell's law, we can find out this refraction, the angle of these refractions. So this is the first medium for us, air. This is the second medium, which is the core. The refractive index of core is N2, and the angle that it is making, if you notice, is alpha, or as we call it's a critical angle, we call it alpha c. And towards this side, the value of n is Na, or you can say just N1. Since it's air, we are saying it Na. And the angle that it is making with this normal is theta a. So the other variable is theta a. So we are using these variables in Snell's law. This is the first medium, this is the second medium. So we want to find out this acceptance angle. So acceptance angle is equal to sine inverse of this value. Okay, we are ignoring Na, or we are saying this value is equal to 1 because actually it is very close to 1. So air has the refractive index comparable to vacuum. Okay, not exactly, but comparable, since it will make very small difference in the angle, so we are kind of ignoring it over here. So we say this value is equal to 1. So to find out this acceptance angle, we take this value, and we already know what the value of alpha c is. We have already found out the critical propagation angle. Okay, so if you know the critical propagation angle, you just put this value over here and you can find out the acceptance angle. And if you notice from this figure, the acceptance angle is actually not just this one angle, but in fact these are the two angles, because light can not only enter from this side making this much angle, but also from this side making an angle like this. Okay, so the total angle that is acceptable, or what we are calling acceptance angle, is actually 2 times theta a. So usually if you read some data that says the acceptance angle is, for example, 40 degrees, then it actually means 40 degrees on this cone. Okay, and if you want to find out only this specific angle from this side to this axis, then it must be 20 degrees, because 40 degree means the angle that this cone is making. Okay, so this 2 theta a is actually the acceptance angle, and if you want to find out theta a, just divide this value by 2. Okay, so the light that is entering in the cable within this angle, within this acceptable angle, will actually experience total internal reflection, and the remaining light that is probably entering, for example, this side. Now this angle is very large, and once it enters the cable, so if this is the cable, so once, for example, it enters the cable, sorry for the poor drawing, you'll notice that the propagation angle, which is the angle that this imaginary line makes with the ray of light, this is very large. Okay, so this angle is actually very large. So we discussed that the critical propagation angle is an angle that is very small. We require light to be very flat, so this angle should be very small. So this angle is actually very large. So if light is falling from this direction, then it will not be able to achieve the critical propagation angle that is required, and then it will not be able to achieve the critical incident angle that is required, and it will not experience total internal reflection. So light that may enter from this side will actually be lost in the fiber optic cable. Okay, it will be refracted out of this cable, and we will only see this value. Okay, so this is or we will only see these rays of light that are passing through this acceptance angle. So we want to find out the acceptance angle. For the same example that we discussed previously, we have the same refractive indices. So all we need is this critical propagation angle. So we already know the critical propagation angle from the previous exercise. We just plug in this value and the answer comes out to be 14.033 degrees, and again we want to multiply this value by 2 because the critical acceptance, or the acceptance angle, is actually twice of this value, the angle of the cone. So this angle comes out to be 28.07 degrees. Okay, so this much light will actually be accepted by the fiber optic cable. So if this is the fiber optic cable and light is, let's say, falling from all possible directions, then only this small portion of the light that is entering from 28.07 degrees will be accepted inside for communication. The other rays of light will be refracted out of this fiber optic cable. Okay. So since we know the importance of this acceptance angle, or as it says in this example, cone of acceptance. So these rays of light are actually acceptable for communication, and the other lights will escape this fiber. So we know that this angle is actually important. So this angle, which we call angle of acceptance, we give it a number, okay, and we give it a number of sine. So sine theta A is a number that is called numerical aperture. So if you have some experience with cameras, or you have maybe you know just some basics of cameras, so the opening of the camera lens is actually called the aperture. So if the lens open only a small amount, we say that the aperture is small. And if the lens in the camera open a lot, I'm talking about a camera with an aperture, not a digital camera as in your mobile phones. So for example, the DSLRs would have this opening aperture. So if the opening aperture is very this hole, or this opening for the light is very large, we say that the aperture is very large. So the numerical aperture, this value NA, is large when this opening is large. So when this opening is large, for example, it is, let's say, 80 degrees. So 80 degree means from this angle to this angle, it can make an 80 degree angle. Okay. So notice this is theta A. This is not 2 theta A. This is theta A. This is the angle, not from the cone, but from this range, from the center line. Okay. This is not the angle of the cone. In fact, it's the angle from the center line. So if this angle, you can say, if light is entering from this side, it is making a very large angle, let's say 80 degrees. So sine 80 is actually a large value. Okay. And supposedly, let's say light that is entering from the 90 degree angle, which seems like practically impossible because it is perpendicular to the surface. So I don't know how it will enter inside the medium. But let's say this magical fiber actually accept this lights. So this light that is entering from this 90 degree angle, and somehow it enters this cable. So this angle is then 90 degree angle. So the sine of 90 is equal to 1. So the maximum value that the numerical aperture can have is 1. So usually it will be smaller than 1. So for example, this angle might be very small, the acceptance angle might be very small. So this acceptance angle might be very small, for example, let's say 5 degrees, which is a very small number. So the sine of 5 will be a small number, not exactly 0, but something very close to 0, because it's a very small angle. So the answers that you can see of numerical aperture would vary from 0 to 1. Again, both these values, the extreme values, are not possible, because an angle of the numerical aperture of 0 means none of the light is actually accepted, and the numerical aperture of 1 means that all of the light that can possibly come near the surface of the fiber optic will be accepted. So obviously these are the extremes, but practically the numerical aperture is between 0 and 1, depending upon how big this opening is. So the bigger the opening, the bigger the angle, and the bigger the answer of the numerical aperture. Okay. So this numerical aperture actually summarizes this value for us. So this numerical aperture tells us that how much light will actually enter. So how many rays of light can enter. These rays of light, all these rays of light that are entering through this angle, they will be accepted. They will maintain the critical propagation angle, and then they will maintain, or they will follow the critical incident angle, and then eventually they will experience total internal reflection. So all these rays of lights are welcome. So this numerical aperture value is important for us because it summarizes the behavior of this whole fiber optic communication, or the rays of lights that can travel inside the medium. So this one value only, numerical aperture, actually tells us a lot about what kind of light can travel inside the medium. Okay, so this is one value, but it's telling us something till the end of total internal reflection. So just one value, but describing a lot. So as we saw that the numerical aperture is equal to sine theta A, which is, this is the acceptance angle. So we already used this equation previously, where we had this NA, where we assumed this value was equal to 1. So NA sine theta A is equal to N1 sine alpha c, which is following from the Snell's law, and we already know that this critical propagation angle is equal to this value. We have already also found this value, so let's plug this value in this. So sine theta a comes out to be n1 into square root of 1 minus n2 n over n1 whole square. Okay, so if you take this value of if you square this value and also take the under root and now take this value inside the square root, this is the result that you will get. Okay, so sine theta a is equal to this value. So we know that sine theta a is actually the numerical aperture. So this means that numerical aperture is actually square root of n1 square minus n2 square. So the numerical aperture, which I said is actually a kind of a summary for us, because it is telling everything to us from acceptance angle to the propagation angle to the incident angle and telling us all about the total internal reflections. This one value is dependent upon the two refractive indices n1 and n2. So this is the importance of you can say the refractive indices, that all these angles, all these values can be described only by these two refractive indices n1 and n2. So numerical aperture is also dependent upon these two values. Okay, so if you want to find out the numerical aperture of the same cable that we were discussing, a silica cable, so putting in these values, the numerical aperture comes out to be 0.2425. Okay, so this is not degrees, this is not the angle, this is actually a number which is telling how much the light actually falling on the surface can travel inside the cable. Okay, so this is not actually telling you the exact angle that is required, it is actually telling a number that how much light can travel inside the medium. Of course, if you want to find out the angle, you can I'll just go back and you can find out the angle using this value. So you know that the numerical aperture is 0.2425. So just take sine inverse of 0.2425 degrees, and you will get the angle. Sorry, not degrees. You will get the angle in degrees once you find out this value. Okay, so that will be theta a, acceptance angle. Sorry. So now that we can define numerical aperture in this term, so if you notice or give importance to the statement that the numerical aperture, since it is providing a summary of the behavior of light inside the optical fiber, these two values n1 and n2, the refractive indices, have a lot more to tell us. They are briefly summarizing everything using just these two values n1 and n2. Okay, so we define, to make our understanding even more clear, we are defining some more terms. Okay, so the next exercise in these few lines that I'm doing is actually just to make this understanding more meaningful. Okay, so let's just put out some more values. So the first value that I'm putting out is the relative difference in the refractive index. So if you take out this difference in the two refractive index, I am calling this the relative difference. Okay, delta n. So this will always be a positive number, because you notice that this value is always greater than n2, so this number will always be a positive number. So this is the value that I am saying is relative difference. Similarly, if I have defined another term, that is delta, which is the relative index. Okay, so why is it called the relative index? Because it is first taking the differences between the two indices. Okay, so it's just a difference, and one could be 2 and 2 could be 3, for example, and one could be 5 and n2 could be 6. The difference in both cases is 1. So this relative index is actually telling me that you need to find out the difference between the two refractive indices. So in my example, it was equal to 1. The other term, that is n, is actually the average refractive index. So it is the average value of the refractive indices. So if the first refractive index was 1 and the other refractive index was 2, the difference is again only 1, and the average is actually 1.5. Similarly, if n1 was say 5 and n2 was say 6, which is again difference of only 1, the average value would be 5.5. Okay, so in both cases the difference was actually equal to 1, but since the average refractive index is changing, the relative index is actually increasing. It's decreasing because the value of n is increasing. Okay. Also, I've assumed that n1 is 1, n2 is 2, or n1 is 5 and n2 is 6. It's not true values because n1 is always greater than n2. So this was just an example. These are the few terms that I defined. Okay, so delta is the delta is the relative index, and n is the average refractive index. So now what I want to do is that I want to write out this numerical aperture value not using n1 and n2, in fact using delta and n. Okay, so it is right there in the book, you can take a look at it, but I would suggest you that before you look into the book, just try to do this exercise yourself. Try to write down or simplify this n1 n2 in terms of n and delta. Okay, just try to simplify, and if you do, if you succeed, you will end up with this formula, which is again very similar to the previous formula. We have just replaced n1 and n2 with n and delta using these two values or these three values. Okay, so this is what you will end up with. So this is another you can say definition of numerical aperture. Now this definition is also very important because we said that numerical aperture is summarizing the behavior of light inside the fiber optic cable, telling us the acceptance angle, the propagation angle, the incident angle, about the total internal reflections. So if this number is so important, this important number can be just expressed with n, which is the average refractive index, and delta, which is the relative index. Okay, so what does it say? So I'll just read this line so that you understand it very well, that this whole behavior can be summarized like this, that if numerical aperture explains behavior of light in optical fiber, then behavior of light in optical fiber depends upon the average and the differences of the refractive indices. So if I have a core in the fiber optic, and obviously I also have a cladding, and I choose two refractive indices, one this for this n1 and the second refractive index n2 for the cladding, then I can change these two values, and changing these two values will obviously change the average refractive index, and it will change the relative index as well, and eventually it will affect the numerical aperture. So changing these two values will actually try to make me understand that what kind of behavior I am creating by changing these two values. So if you are actually a scientist working on the fiber optic cables, you will try to adjust, hey, what kind of n1 can I achieve, what kind of n2 can I achieve, what kind of n2 can I manufacture, what is the possibility for me. So if I do this kind of refractive index, if they make this kind of refractive index, what kind of fiber optic cable will I end up with? Do I need to increase the average refractive index, or should I control the relative index? What should I do? So these two values can be very important for designing or proposing the whole behavior of light in the fiber optic communication. Okay, so this is the importance of this value, the numerical aperture. So for as it says over here, for silica fiber, this Na value is typically from 0.1 to 0.3. So this is the usual value in most practical cases. And even though we discussed in detail, but it can also be physically, or you can say practically, it can be estimated using this calculation, where P in is actually the power inside the injected inside the fiber optic cable using a light power meter, and P naught is the power observed at the output of the fiber optic cable. So what we can do is we can do a small experiment. We can have a optical power meter. We can see the power of the light. So we have this source, and we place only a very small fiber optic cable, a very small length, maybe just a few centimeters, and we put this inject the light inside this fiber optic cable and observe the power of the light over here. So this power will be called the power inside the cable. And then we place a practical cable, that is, I mean a cable of considerable length, and we observe this power, the optical power outside this cable, and this power is known as power at the output of the cable, P0. So if I take this difference, this value also gives us the numerical aperture. As I said, this is just a practical way or a physical way to calculate this value. Okay, so it will be an estimation. This value will be very close to the true numerical aperture, So if you're not you're a manufacturer yourself, you can actually also calculate the numerical aperture, or you can validate the numerical aperture using such a calculation.